All right, here we go in our next section. This is what we're calling 6.4 Riemann sums. This kind of ends up being a pretty important part of this unit on integration. This ends up being, this kind of discusses where this comes from and why it works. And so this gets at the guts of integration. We're going to use some notation here that we haven't seen in a while or worked with too much yet this semester. So we're going to start off with this. We'll start off with a couple of examples about summation notation. Once we finish with a few examples, maybe hit pause and go through these practice questions on your own. I would suggest that in the next section, the investigation, that you just hit pause and try to go through that investigation on your own as well. And so I will prompt you for that when we get there. So this one starts off with a symbol that we saw earlier. This is called sigma, is the Greek letter sigma. It's their capital letter, their uppercase letter for sigma. And it's used quite a lot in mathematics, and it's used for summation notation. So sometimes we call it sigma notation. Some people call it summation notation. That more describes summation notation. That essentially is what this notation is doing, is it's adding up all of these terms that it gives after your summation sign. So in this first one, this one says this is the summation of 1. And this is what we are summing. Now we also have these other pieces going on. We have I equals 1 below it, and we have n above it. And that tells us how many terms we are going to add up. Whereas the 1 tells us what we are adding. And in this case, this notation essentially means that we're adding 1, plus we're going to add 1 again, plus we're going to add 1 again. How many times are we going to do that? We're going to do that n times. And so that's why this is equal to n. What this number here, I is equal to 1, is telling us what we are starting with. We're starting with I is equal to 1. And when I is equal to 1, that's this term here. Then we'll let I will equal 2, and then it'll equal 3, and then it'll equal 4, and then 5, and then 6, and then 7, until we get up to n, which this will be the last one. So if this number up here was a 10, that means we would just have 10 terms of adding 1 together. We would start with I is 1, and we would crank it up by a notch every time we added another 1 until we get up to 10, and then we stop counting them and adding more. So that's really all that this is saying, is we're going to add 1 n times, and so it does add up to n. In fact, for any constant c, we can keep adding c plus c plus c plus c. How many times? Well, we're going to do this one. I is equal to 1. I is equal to 1. We're going to add c. I is equal to 2. We're going to add c again. I is equal to 3. We're going to add c. And we're going to keep going. How many times? We're going to do this n times. And so this total is c times n. All right. And then this is where it starts to get a little bit more interesting. Now we're going to add up I, and I is going to start at 1. And then we're going to crank it up by a notch. So I starts at 1, and then we're going to have 1 more. And so now I is 2, and so this is just I that we're adding. So we're adding 1 plus 2 plus 3 plus 4. And how far do we go? We go until I is equal to n. Now, it just so happens that we have this nice kind of formula for summing together natural numbers, 1, 2, 3, 4, 5, 6, 7, all the way up to some number n, that it ends up being this formula, n times n plus 1 all over 2. We're going to use that identity, that the summation of I from 1 to n is equal to this. We're going to use that a bunch of times in this unit. In this next one, we're going to add I squared. So when I is 1, our first term is 1, when I is 2, I squared is 4. 3 squared is 9. 4 squared is 16. How far do we go? We go until we get up to n squared. And it just so happens that we have this nice formula for the summation of I squared from 1 to n is n times n plus 1 times 2n plus 1 all over 6. And then our last identity that we're going to look at is I cubed. We're going to sum I cubed from 1 to n. It would be 1 plus 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. Go all the way up until when I is n, that will be our last term. Our last term will be I cubed, so that ends up being n cubed. And if we add all of that together, we end up with this formula here, or sometimes the one before it, n squared times n plus 1 squared over 4. All right, I do want to go through one of these practice ones together just because, just so you can kind of see what I'm getting at, what is needed here. Also because I think in the solutions, there's a typo in the solutions, so let's bypass that. If we have the summation of 2 plus I all squared, where I goes from 1 to n, that means this is equal to the, well, let's just algebraically, let's simplify this a bit for us. Let's square out 2 plus I, and so we have the sum of 4 plus 4I plus I squared. So just squaring that out, where I goes from 1 to n. So we have the summation of this. Well, if we think about that, we're just adding each of those terms. We're letting I equal 1 and then 2 and then 3. Because addition is commutative, it doesn't matter the order that we add these things together. We could break this apart into the summation of this constant 4 when I goes from 1 to n, plus the summation of 4I, where I goes from 1 to n, and then plus the summation of I squared. We can do maybe a couple of things to simplify this. This question is just asking for you to express this in terms of monomial summations. So we could simplify this. The first one, the summation of 4 plus 4 plus 4 plus 4, n times, is just 4n. But really what we're doing here is let's factor that 4 away from 4i. Let's bring it outside of the summation, because it's 4 times I. So that would be the sum of 4 plus 8 plus 12 plus 16, which would be the same as 4 times the summation of 1 plus 2 plus 3. And so this ends up being 4 times the summation of I plus the summation of I squared. And that's really all that you're required to do in practice question 1. It's just this. If you left that first term as the summation of 4, that would be okay too. Later on, we're going to start to simplify by dropping these identities, n times n plus 1 over 2, or n squared times n plus 1 squared over 4. So we will drop those into place when you're getting through question number 2 and you're evaluating these, and then further into this unit. All right, so I'm going to give you some time. We'll maybe hit pause here, and then once you've gone through these, let's join me, and we'll go through this investigation. All right, so I hope those summation questions went okay for you. Let's get into this next section. This is still 6.4. This starts off with an investigation that I'd like you to attempt more or less on your own to start with and see how far you get with this. So I'd like to encourage you to maybe look through this, and you're gonna look at these 3 different examples below and try to go through questions 1, 2, and 3 like this. And regardless whether you're having trouble or not, if you've made it through all of this or not, if you want to go through this with me, hit pause, join me back here in a minute, and then we can go through this together. What this is doing, is this investigation is doing, is it's going to look at these curves similarly to what we've done before when we looked at slope. So when we looked at slope, remember that we took a tangent to a curve, we took a secant to a curve, and we took these 2 points that got closer and closer to each other until we took the limit of the distance between these 2 points was essentially 0, and we took the limit of that, and that ended up helping us calculate the slope of the line. We're going to do something that is kind of similar to that here. And this starts off by saying it's very important that for these following questions, even if it's evident to you, you show all of your work. The easy questions will help you figure out difficult questions later on. And you'll see what we mean by that when we get to the end of this section. All right, so to go through this, we're going to go through question 1 and look at graph 1. And question 1 says this: using graph 1 on a separate piece of paper, calculate the area between the curve and the x-axis from x equals 1 to 5 using 4 vertical rectangles by answering the following. Okay, so let's start this off by doing this on this graph, and we want to find our area between 1 and 5. So from here to 5, and we're wanting to find our area under that curve and above the x-axis. We're going to start this off by making rectangles. And this first rectangle kind of tops out and it hits this line at a height of 1. When x is 2, it seems to go to about a height of 2.5. When x is 3, we seem to have a height of 5 here. When x is 4, we're going to call this about 8.5. And then when x is 5, we end up with a height of 13. And so if I want our area under that curve, it's just going to be the sum of the area of those 4 rectangles. Question A says, what's the length of the base of each rectangle? How would you determine this and write a formula? So quite clearly, the length of the base of each rectangle is just going to be 1. How could we show that mathematically? Well, we would take the right bound, which is 5, and we take the left bound, which is 1, and subtract them. We're going to divide that by 4 because we have 4 rectangles. So this ends up being 4 over 4, which of course is 1, which of course is the width of those rectangles. That seems to be all good. If we estimate the height of those rectangles, we said the first one was 1. The next one was 2.5. Our following one was 5. The next one was 8.5. And our last line was 13. Those were the height of each of the lines at 1, 2, 3, 4, and 5, respectively. To write each height of those rectangles in function notation, then we would say f at 1 is 1, f at 2 is 2.5, f at 3 was 5, f at 4 was 8.5, last one f at 5, which isn't really one of the rectangles, that just ends up being the height of our right bound, is 13. D gets at the fact that we are trying to calculate our total area by creating a formula. Area is length times width. And we're being asked bonus marks if you can write this using function notation for height. So our first rectangle's height is f at 1. Its width is 1. We're going to add that to the area of the next rectangle. The next rectangle is f at 2 in height times 1 in width. Our third rectangle is f at 3 in height times 1 for width, and then f at 4 in height times 1. Adding those together, this just ends up being 1, 2.5 times 1 plus 5 times 1, 8.5 times 1. And when we add that all together, this ends up being 17. So the important part of this is realizing that step here, that the height of the curve for each of these rectangles is going to be your height of each of these individual rectangles. And then in E it says explain whether or not the area you found is an overestimate, an underestimate, or an exact calculation. Well, if we look at what's going on, this looks to be, it's going to be an underestimate, because if we added up all of these areas, and we got 17 for the sum of these, well, that's all fine and good for that to be 17, but we are missing large parts of our area here. We're missing all of that stuff that's in orange. On the next page, it asks us to do the same, but we're going to do it with 8 rectangles. So we're going to do this on the next graph, and we're going to break it into 8 rectangles. If we're going to break this into 8 rectangles from 1 to 5, so here's 1 on the left, here's 5 on the right again. The distance between 5 and 1 is 4. So if we're going to break this into 8 rectangles, we're going to look at f at 1.5, and f at 2, and f at 2.5, f at 3. We're going to break it into narrower rectangles. And they're going to look like this. This first one is still going to be at a height of 1, 1.5, 2.5, 3.5, and we're just estimating here. And if you went through and did this investigation, you had slightly different numbers. If you called that 3.4 or 3.6, that would be okay too. 6.5 is f at 3.5. F at 4, we end up with a height of 8.5 and 10.5 for our last one. So, how wide is each of those rectangles? What's the length of the base of each of those rectangles? Well, it's a half. How could we show that it's a half? Well, we take our right bound is 5, we take our left bound, which is 1, and we're dividing that into 8 rectangles. This ends up being 8. 0.5 is what we have for width. What's the approximate height of each of these rectangles? Well, we just kind of went through these. Again, perhaps yours are slightly different numbers, but in general, it's going to be about these numbers: 3.5, 5, 6.5, 8.5, 10.5. To describe each of those with function notation, well, that first happens when x is 1, so let's call that f at 1 is equal to 1. The next line happens at 1.5, and it goes to a height of 1.5. Third one happens f at 2, 5, f at 2.5, 3.5. 3 is 5, f at 3.5. So the x values are going up by a half. The y values seem to be increasing at a greater and greater rate, which makes sense because it looked like the line was getting steeper. F at 4 is 8.5. Last one, F at 4.5. In part D, just like before, we're going to find our total area and create a formula for this. So area, we end up with, for our first rectangle, is F at 1. Is our width 0.5 plus F at 1.5, 0.5, 2 times 0. And we could probably just get away with, we've shown that there's a pattern here, having each of those x values as inputs into F. And our last one ends up being F at 4.5 actually, times 0.5. We common factor out 0.5, leaves us behind with F at 1 plus F at 1.5, 2 plus dot all the way up to F at 4.5. We end up with 0.5 times 1 and 1.5, 2.5. This is probably more detail than we need in here. Might as well go ahead and finish this up and actually calculate. We have, if we add all these together, we end up with 0.5 times 39. So we end up with 19.5 square units. Keep in mind that when we did this with graph 1, we got an answer of 17 square units. We said at that point it was an underestimate for our graph. Now we get 19.5, and if we look at what the graph looks like, we still have an underestimate. So now we have this area of 19.5 if we shade in all of these rectangles. Still an underestimate, however, because we're still not counting these, albeit smaller pieces, but albeit there's more of them, but they are small. So we can see that this ends up being an underestimate still. And we end up with 19.5 square units. He's asking us to explain how this works, so maybe a little bit more detail in here. Underestimate, as we are left with areas unaccounted for. We have a better estimate than we did in part 1. We have a better estimate now. We have smaller areas unaccounted for. And then what this is all leading towards is part G. How could we continue to determine more accurate estimates for area? Well, of course, we could make more rectangles. smaller bases. Now, some textbooks and some professors and some people that teach this will get you to underestimate like we've done, but some will actually look at an overestimation by taking the right side of the triangle leading up to this. And some will even look at making trapezoids. So connecting these 2 points and then making our not rectangles, but making trapezoids instead ends up being pretty accurate, even just with these a finite number of figures that we're adding up together. Turns out it's not going to matter really, because we're going to add up, as you can guess, we're going to add up together infinitely many of them. Question number 3 says, looking at the third graph, we've got the same function, but now without a scale, and we want to do this in general. We have this curve from A to B, and so we're wanting to break this up into rectangles. And how do we do this? If we have our right bound is B, our left bound is A, and if we divide it by n rectangles, then this ends up being B minus A over n. We're going to call that delta x, because that represents your change in x every time you have a new rectangle. Using our function notation, then the heights of these rectangles, the first one will be f at A. The next one will be f at A plus a little bit. And what we're going to do is we're going to move to the right by delta x. So it's f at A plus delta x. Our next one, it ends up being f at A plus we're going to move over 2 times delta x to have our third left bound. 3 delta x, and so on. Our last one ends up being not n, it's the one before n. So n minus 1 times delta x ends up being our last height. Just like when in our last question, we didn't use f at 5, we used f at 4.5 for the height of our last rectangle. So for part C, to calculate our total area, we end up with, similar to before, our constant that we're going to factor out is the delta x, and then adding up each of the heights, f at A plus f at A plus delta x, 1 delta x, plus f at A plus 2 delta x, plus, and continue the pattern until we get to f at A plus n minus 1 delta x. So those are the height of each of the rectangles, multiplied by the width of each rectangle out front here, gives us our total area. In part D, thinking back to our work on series, what could we use to add up the infinite number of terms? How could you incorporate this notation into your work for all of those heights? So what we end up with, each of the x values, it ends up being x sub I. If we start with A, and then we add I times delta x. So that's going to represent each of the x values. So each of the heights ends up being f of each of those terms, which is f of x sub I. I is going to go from 1 to n. So that's the summation of the heights. To get as many rectangles under this curve as possible, we're going to make each base as small as possible. So we have for our limit for the bases is b minus a over n, which is what we used to calculate this before. N gets to be larger and larger, so n is going to infinity. When we do this, that's telling us that we are taking infinitely many rectangles that are infinitely thin. And so all of this put together, we end up with the summation as I goes from 1 to n, the limit as n goes to infinity, b minus a over n. So that is our width times what we have for heights. And as we start to formalize this, let's bring that limit outside of the summation. And we're going to take the limit as n goes to infinity of the summation as I goes from 1 to n of the heights. We usually would write this first. X sub I is going to go from 1 to n times delta x, which is the width. We should define this in here, where x sub I is equal to a plus I times delta x. There should be a note in here that notice that what happened is we should actually be running with I goes from 0 to n minus 1. Instead, we're calling it I goes from 1 to n. Adding 1 to each bound isn't going to matter at all. So just noticing that I equals 0 to n minus 1 will give the same result. As I, just renumbering, that I goes from 1 to n. So what this ends up doing for us, it gives us this formula of how we can find the area of the whole curve, not having to underestimate it all, because we're going to look at infinitely many. So now let's revisit f of x equal to 3x plus 2 on the interval from 1 to 3. So what we end up with is a sub n, area, going from 1 to n of xi delta x. What do we know about these things? We know that delta x b minus a over n. In this case, right bound is 3, our left bound is 1. We're going to leave this as n because we're going to take infinitely many of these. So let's just simplify this to 2 over n. We have x sub I. The definition of x sub I is just this a plus some number of changes in x. So a plus I times delta x. We've just found what delta x is. And we know that a is 1. So it ends up being 1 plus I times 2. Let's call it 2i over n. That comes from what we just found to be 2 over n. And one last step before we get going in this. F of x sub I then, therefore, our function is 3x plus 2 So it's now going to be 3 times that xi, which is 1 2i over n plus 2. We can simplify this and call this 3 plus 2 is 5. Multiply that 3 into the brackets. We have 5 plus 6i over n. So that's all said and done. Now we go back to our area formula. So a of n was equal to the summation of fxi times delta x. I is still going to go from 1 to n. And it ends up being 5 plus 6i over n. Those are your heights. Your width is 2 over n. We can factor out this 2 over n. We can pull that out of the summation. The summation just depends on I. And so this is the summation. I goes from 1 to n of 5 plus 6i. Let's break that apart into 2 terms. And we end up with 2 over n bracket. The summation as I goes from 1 to n of 5 plus the summation as I goes from 1 to n of 6i over n. Now we can use those summation identities that we dealt with earlier. And the summation of 5, as I goes from 1 to n, 5 plus 5 plus 5 plus 5, how many of them? N of them. Ends up being 5n. This second term, let's factor out, let's bring outside of the summation, this 6 over n, and now this is just the summation of I going from 1 to n of I. Now we have an identity for that, which is why we did at the beginning of this section, the summation of from 1 to n, so 1 plus 2 plus 3 plus 4. Simplify this term. It simplifies to n squared plus n over 2, or n times n plus 1 over 2. We are almost there now. We're going to continue to tidy this up. This ends up being 5n. If I factor out n of that numerator and divide it with that n in the denominator, this ends up being 6 times n plus 6 over 2, just dividing out a factor of n. And then tidying this up a little further, 2 over n, we end up with 8n plus 3. Which ends up being 16, 6 over n. So remember that this all along has been your area dependent on n. Our full area now ends up being the limit as n goes to infinity. 16 plus 6 over n. So we could have had that limit in our notation all along and just called it area instead of calling it an. Ends up being a lot more writing to do. So if we just call that the area depending on n, and coming up with this formula. Now let's take our limit as n goes to infinity, and we can see that when n goes to infinity, this area ends up being equal to 16. All right, one more. Let's use our Riemann sum to find our area under the curve of y equals x cubed. Maybe not a bad idea to provide a sketch. This is just a simple cubic function. But we are wanting the area as x goes from 0 to 4. So we are wanting to find this area. Start off with our formula that area ends up being the sum as I goes from 1 to n. I pause. So we end up for area being the sum. I goes from 1 to n of the heights, which is f of xi of each of the rectangles, times the width of each of the rectangles, which is delta x. We need to define what each of those pieces means. So let's start with delta x. That is just your upper bound minus your lower bound. So 4 minus 0 over n. So depending on how many rectangles we're making, that will be the width of each rectangle is 4 over n. X sub I ends up being each of those x terms. It ends up being a, which is the start, left bound, plus I times these widths. We end up with 0 or I over n. F of those values, f of x sub I, now ends up being this function, y is equal to x cubed. So we take 4i over n. We're going to run it through our function f. So 4i over n all cubed ends up being 64 I cubed over n cubed. All right, now let's revisit our area formula. So an ends up being the sum as I goes from 1 to n of 64 I cubed over n cubed. And then we're multiplying that by the width of each, which ends up being 4 over n. The stuff that isn't relevant to I, we can take outside of the summation. So 4 times 64 is 256. We have over n to the 4. And what's left within here ends up being i's goes from 1 to n of I cubed. Now, if we go back and we look at our identities, we have the summation of I cubed. Ends up being n squared, n plus 1 squared over 4. Simplifying this a couple steps, 256 over 4, 64, n squared over n to the 4 is n squared downstairs here, and we have plus 1 squared upstairs. That is a sub n. for our area, we're wanting to take our limit. So let's pull that 64 out. Ends up being the limit as n goes to infinity. Of n squared, 2n plus 1 over n squared, just squaring out that bracket, which ends up being equal to 64. The limit, simplify each of these terms, ends up being the limit of 1 is 2 over n, 1 over n squared, which we've seen before. When we evaluate that limit, that ends up being 1, 0, 0. And then we end up with 64 square units. And that is Riemann sums. So there's a lot in this video. I would encourage you to attempt some questions, but maybe go back and revisit this. And good luck. Thank you.